sorry for the delay. So we still didn't make it work. So the speaker had to go back to do the real demo. So, but anyway, so welcome to San Francisco Big Analytics. My name is Chester Chen. I also work for GoPro. So welcome to GoPro. So before we start, and so since we're hosting the GoPro, so I have to say a few words on behalf of GoPro. So you know, there's a different departments. Department heads of departments asked me to say a few words about openings. So we have quite a few openings. First one is from IT. IT have I think I have 3 openings. One is the head of infrastructure, you know, the network administrators, Linux groups. For the program management, they want to have a senior technical program manager, so there are openings, so if you're looking for program managers. And also for the engineering, we're looking for DevOps, we're looking for software engineers in our cloud media teams. So if you're interested, you can go to the GoPro website looking for the corresponding stations, or you can just talk to me. So that's from the GoPro side, and I want to thank our coordinator and also the AV engineers Ray back and somewhere. So yeah, thanks to help to bring the food and prepare the space. So sorry to keep you guys waiting. So tonight we've got 2 talks. So first talk is from Xiang Ray is Apache, Spark PMC. He has been working on Spark for a long time. So especially initially working the MLlib, a lot of work done there. And then recently, last 3 years, he was working at Databricks on managing the data engineering team there. Now he's coming back to open source community to put more effort on the Spark machine learning project. Tonight he's going to talk about what the latest development on the Spark related to deep learning. So welcome, Sharon.
Chester, I may need your microphone.
Hi, everyone. It's well, thanks Chester for the invitation and GoPro for just hosting this meetup. Let me try this one. Does it work? Oh yes. Great. So my name is Xiang Ray, and I'm currently leading the machine learning algorithms and performance team at Databricks. And today I'm going to talk about ongoing initiative and in Apache Spark project that try to unify the big data and AI together. The project name is called Project Hydrogen. It's just a name. So how many people here are Spark users? I mean, just use Spark on a daily basis. How many people are learning Spark? Okay. So Spark is currently kind of the most popular engine for big data processing. And around the world, there are many Spark users, there are many Spark developers, and every year, and our company hosts the Spark Summit, and this year we have more than 4,000 attendees, and even across the world, I believe there are so many meetup members on just Spark meetups. And then another question is, how many people are building machine learning models and using TensorFlow to build deep learning models? Yeah, so we know that, okay, so AI is kind of reshaping our life, right? You see many things, self-driving cars, and the next smart things, and IoT, and that really just start changing our life. And yeah, so if you really just want to try Spark or try out TensorFlow and follow some tutorials and to learn both of them, and Databricks Community Edition is kind of the best place to start. And this is a free version of our product. You can just easily sign up and then just get a mini Spark cluster and follow many tutorial notebooks online. This is just one example, just TensorFlow tutorial and using MNIST for just recognize digits. So today I'm going to talk about these 2 communities. One is the big data community, and the other one is AI community. In the past few years, I saw, well, for the big data community, they spent a huge amount of effort trying to handle complex data scenarios, reading data from different places, and support streaming data and large large data processing. And for the AI community, and they have been working extremely hard on just making training deep learning model faster and make deep learning networks can be applied to multiple verticals. And so it's basically both communities are working on more complex scenarios. This is a summary slide I want to show the past of how each community come to just from the past to here now. For the Spark community, it starts with Databricks. Actually, this is just a logo at the bottom of the slide. And it starts from the UC Berkeley AMP Lab, and that's the birthplace for Apache Spark. And Apache Spark just used the MapReduce framework that's invented by Google and made it popular open source by Apache Hadoop. And initially, it only has this RDD interface, and in Scala, and then later in Python, Java, R. And then, we made this data frame-based APIs to make data scientists really easy to use Spark. And the community helped build more than 50 plus data sources, and literally Spark can read data from anywhere, and in a very easy approach. And then on the machine learning side, we also just designed this ML pipelines API, so for people can easily construct a machine learning pipeline consisting this feature engineering, model training, hyperparameter tuning, as well as just you can also export the entire pipeline to disk. And after that, there's a major project initiative called Project Tungsten. It's really the aim at bringing Spark performance to bare metal performance and deliver the best-in-class scalability and performance using code gen and off-heap memory management, make Spark much, much faster. And then in the recent release, that's Spark 2.3, we have this structured streaming and continuous processing as well as Pandas UDF, just to make Python users and easy to use Spark and make the performance much better for Python users as well. So this is kind of the Spark community part. And then on the AI and the machine learning community, and you can see people start with very primitive libraries like NumPy, SciPy, right? So you can only do just basic create a matrix and do some matrix multiplication. And there are also R, and they're used by many statisticians. And after that, we saw some dedicated machine learning libraries. You can only just build very limited set of models, but they can really do a good job. Like linear for linear SVM and logistic regression, and the GeoNet for generalized linear models. And then, it came scikit-learn. It's made really just a general purpose machine learning package. People can build many models, and people can just do feature engineering inside the same package. And there are also just other libraries like XGBoost and GraphLab for special purpose. This is more like a traditional machine learning, right? So just traditional models. And then we saw these deep learning packages like Caffe, PyTorch, and then TensorFlow came, and it became super, super popular. And on top of TensorFlow, people actually, if you look at the progress, people did very similar things compared to Spark. The first one is Keras, similar to the data frames API in Spark. Make really, really easy to use TensorFlow, right? So you can just describe your network layers easily. And the other one is this TensorFlow XLA. They use the accelerate this linear algebra operations and make the performance much, much better. And then on top, and this is kind of like the recent 201 or 2 years. And people start just doing a lot of distributed deep learning training because people need to apply deep learning on a really, really large data set. They need to handle just or they want to have much, much faster training time. So people don't want to wait for 1 week just for a model, and the model may turn out to be bad, right? So then they need to spend another week and to get a good model. That's not what people want. So you want to just start a training and get a coffee and check the result back, right? So, and people start doing this distributed deep learning, and there's frameworks like Harvard from Uber. So essentially you see those two communities start with very just low-level primitives, and if those primitives can just really just make things feasible to do, and then they start building up both performance and usability, right? So make APIs easier to use and make the performance and scalability better. And now both community kind of across here is both of them need to handle the distributed scenario and managing distributed data sets and doing distributed deep learning. So I would say first of one is both of the efforts are non-trivial. And first, this is a kind of a copy from Google's newspaper in 2015. And they described their machine learning framework. And they need to build many kind of infrastructure and to support an end-to-end machine learning pipeline. And writing code is usually just a small component in this large framework. So building AI is definitely just making machine learning to work is definitely not an easy task. And so another one, but however, is at Databricks, we have many customers, and they process a huge amount of data. And sometimes you can imagine how much data just companies collect every day. And I talked to those customers and asked them why they collect such a huge amount of data and why they just do this data processing every day. Is the majority of the answer is, I want to use machine learning, I want to apply AI, and to boost my business, right? So, and for example, I list hotels.com here and the Rare Games, and they all use the data they collected and then build machine learning models to improve the user experience. So people basically just process big data, and the main goal is actually just AI and machine learning. And this is why we see this effort from Spark community and to integrate with those deep learning and AI frameworks in the past. And like a Cafe on Spark, TensorFlow on Spark from Yahoo, and Big DL from Intel, and Spark NLP from Johnstone Labs. And we also, at Databricks, we maintain a couple of just third-party Spark packages and to make the integration better. And so on the other side, this is people processing just big data for AI. And on the other side, AI, well, if you want to build a good machine learning or AI model, you definitely need big data eventually. And this picture is kind of super popular on the internet. And you just compare, give you a kind of rough idea about why deep learning is better than the traditional machine learning algorithms. And it's more about the scalability. And when you use traditional machine learning, because the model is usually linear or just very simple, it doesn't really scale up with your data set size. That means after your data set size reach a certain amount of number of samples, and you don't see just a significant boost from your traditional machine learning algorithm. But with deep learning, because the deep neural networks can represent a much complex model, and if you tune it really well, it can actually scale much, much better. So, but in order to beat traditional machine learning algorithms, that means you need more data. You need to feed more data into the training process, and then you get a better model out. That's why, and the AI community see the need of handling big data. And then we also see the effort from the TensorFlow community. For example, they build this tf.data package and the tf.transform package, and to provide some simple primitives for user to easily handle the data set and just do some data transformations. They also offer Spark TensorFlow connector, so people can use Spark to process the data and then just save the data into Tensor TF records format for deep learning training. So those are, you see this, both community kind of need effort from each other. And so we see this overlap here, and we try to see what are the potential difficulties and for people to use both big data and AI. And this came the Project Hydrogen initiative we are talking about here. If, let's say, I want to give you a simple example to show the difficulties here. If you are a data scientist, you build some machine learning models. Those are the two most common scenarios you need to handle. The first one is I need to read some training events from a production database, right? So production data warehouse in my company, and then I need to train a deep learning model. But because the data is huge, and I need a distributed training here. And the second scenario is after I train this deep learning model, I want to make predictions, right? So I want to, for example, just apply the model to a data stream and to enrich the data and with some predictions and let downstream application to handle the enriched data stream. So basically, model training and the model inference. Those are the two common scenarios, and we need to just handle here. The first one is distributed deep learning training, and you may load data from a production data warehouse, and they may be Databricks Delta, Amazon S3, Kafka, Azure Blob Storage. There are many of them, right? So in order to load data and from those many places, Spark is kind of the definitive choice here. And because Spark has this 50+ data sources, and you can read from just a CSV, MySQL database, Hive, almost everywhere. So the answer here is definitely Spark. And then you go to the distributed training part after you load the data. And now you need a distributed GPU cluster because GPU is definitely provide much better performance when doing deep learning training. And here you may have other answers, just a couple answers like a Harvard, distributed TensorFlow, distributed Keras. So it seems natural to get two answers for different stages. But then the question is, how are you going to set it up? Just remember the previous slides I showed Google outline the infrastructure they have for machine learning. And then you need to think about how you do this infrastructure setup. First, you need a Spark cluster to load your data, right? So because you use Spark here. And then you need a GPU cluster to do the distributed training, and you save the data somewhere. So this cluster can save data, that cluster can read from this storage. But however, you need to manage the glue code. You need to learn how to submit a job to a Spark cluster, and how to submit a job to a GPU cluster, how to monitor the progress, how to just link them together. So you need to maintain this glue code as a data scientist. But as a data scientist, you should focus on really just a model training, make your model better, rather than just maintaining this glue code. So, and then the second scenario is this streaming model inference. Let's say I'm okay with having two separate clusters. I can manage this glue code. But then, when you go to model inference, what happens is you have a streaming data source. Usually this is Kafka or maybe Kinesis. And you load the stream, and you apply the deep learning model and make predictions, and then send the results back to the stream sink, maybe a Kafka again, right? So now, if you think about this setup, for prediction, you need GPUs, right? So this one should happen on a GPU cluster for the best performance. But how do you load the data from Kafka? TensorFlow doesn't support it. So definitely, you still need Spark to do the work here. Spark can load easily from Kafka. But then, are you going to load in the Spark cluster and send the stream to the GPU cluster? Then you need to define your own kind of communication protocols here. And that's maybe even harder than maintaining the glue code. And it would be ideal if you can do everything on the same cluster. right? So the same cluster can load data using Spark, can do distributed deep learning, and then you don't have to maintain glue code, you don't have to design your own communication protocol. So that would be the ideal case. And have a hybrid Spark and AI cluster, and then you can just say, streamline your work. Well, if this works, and I don't need to just give the talk here, just it doesn't work out of the box. I have a small demo here, but I can leave the demo just because I need to go there to do the demo. I have 2 demos, I will merge them together. So, but let me briefly talk about why, well, it doesn't work. This is how Spark works. Spark implements the MapReduce framework, and in MapReduce, and when you schedule jobs, each task is kind of independent of each other. You can say, I have a task slot here, and just run this task. And then I have another task slot, I can run the next task. So the task can be scheduled independently, and that's why Spark can manage this really, really large data sets. However, for distributed deep learning training, it's very different. So the nodes need to communicate, coordinate the computation and communicate with each other frequently. And in order to just say make progress on the training, so they cannot be scheduled independently. They have to kind of work together with each other. And in Spark, if a task failed, Spark can easily say, let's restart this task. But if in distributed deep learning training, if one task failed, depend on the implementation, but very likely the entire job will fail, and you want to restart everything and maybe load previous checkpoints so you don't lose much progress. So this is a fundamental difference here. And that means Spark cannot really schedule a deep learning job. If you run this distributed deep learning job on a Spark cluster, Spark doesn't know about this workload. So it's something like just someone else SSH into your cluster and run some job, and you don't even know that. And what happens is, if you continue running some Spark job, and the Spark job may schedule a task on a node that's already running this deep learning job. So that means you you need to compete with the CPU memory, GPU memory network. So that will either crash your workload or slow down your workload. So this is the kind of the main challenge if you want to build this hybrid Spark and the AI cluster. And we thought about this, and then this is why we proposed this project Hydrogen. And it has 3 sub-projects here. The first one we call barrier execution mode. It's basically say, let Spark be able to handle the distributed deep learning workload. And the second one we call optimized data exchange, to make the data exchange between Spark and AI frameworks much, much faster and easier. The last one is called accelerator-awareness scheduling, to make Spark be able to recognize the GPUs installed on just the Spark worker nodes. First one is the barrier execution mode. As I mentioned, the major difference between Spark's MapReduce mode and the deep learning training is Spark can just schedule tasks just independently, but for deep learning, you have to launch maybe 4 nodes together and start the training job and then stop them together. So in Spark 2.4, we implemented this updated Spark job scheduler, and we introduced this called GON scheduling. GON scheduling means you schedule some nodes together, and so Spark can actually recognize this distributed deep learning workload, so they can be run as a Spark job. In this way, while you don't need to worry about someone else is running some deep learning job on this worker node, and at the same time you're running a Spark job on the same node. This is just briefly walk through the APIs. And you have an RDD in Spark representing a distributed data set. And to tell Spark, when you compute this RDD, you have to launch the tasks all together. And you just call barrier and RDD.barrier, and then map partitions will tell Spark to say, hey, please run this task and all together. Inside this task closure, you can actually get the current context, which tell you about what other nodes are running for this task, for this job. So then, well, when you try to coordinate, just try to embed this distributed deep learning job inside Spark, and you need certain just some tooling to coordinate the work. So for example, I want to write some just training data into disk, and then I need to tell all the workers, hey, well, please write the current partition out to local disk, and then we are going to start a distributed training. But there may be some data skew, and some may be faster, some may be slower. But to ensure you have a successful training, and you kind of need to say, hey, let's put a barrier here, right? So everyone just, when you hit this barrier, and please stop until everyone else just finish and reach here, and then go. So that's why we call this a barrier execution mode. And if people are familiar with the MPI, the traditional MPI pattern, this is just an MPI barrier. And then in order to embed this distributed deep learning job, so we also need to provide some sufficient information so we can actually launch this deep learning job. The very important one is the IP address of all the Spark workers scheduled for this job, right? So, and you can get those information, and then you can use MPI to say, hey, let's launch a hybrid training job. But in this way, and after that, well, this command is triggered from only one node. And while this node will SSH into other nodes and then start this MPI job. And then for everyone, you just wait for this job to finish. So before you can release this Spark task slot. In this way, Spark can just can run this distributed deep learning job as a Spark job. So then the scheduler recognizes the workload, they don't crash into each other. So I think it's maybe the time to do a demo so people get more kind of concrete understanding of this Spark scheduling issue. Should I go to the back? Yeah. Let me try. Yeah, I believe you don't need to look at me. you can only look at the screen. Sure, I have the internet. Okay, yeah, this is, I'm using Databricks for this demo. Actually, I don't need to type. Oh. Do I need to? talked about this barrier execution mode and make Spark be able to recognize the distributed deep learning job. And yeah, unfortunately I cannot do the live demo, but there will be some recording online, and I will ask Chester to send out the video link. So in Spark, we also need to do some additional work to make sure Spark can handle different cluster manager and like a Spark, like Yarn, Kubernetes, and Mesos, and this is more about the community work. And the expectation is in 2.4, we are going to provide a basic implementation of barrier execution mode that can handle limited scenarios. And but by the time of 3.0, we plan to have a very, just a kind of like a production-ready implementation. So the second part of this project Hydrogen is called data exchange. Because we are talking about this framework integration, especially big data and AI framework, it would be kind of a magic if we don't need to touch data, right? So we don't need to exchange data between the two frameworks. And let me show you the problem here. And in practice, we need to handle different data formats, right? Someone sends you a CSV file, and your data is just stored in Parquet file, and you have some MySQL database you need to just read from. And then, well, when you reach deep learning, and you need to convert data into TF records, and some use HDF5, that will be just a traditional high-performance computing format, and also include NetCDF. And people also use CSV, JSON, and libsvm. So that means if you want to load the data somewhere and do deep learning, you have to find a way to convert MySQL data to, for example, TF records. And you can definitely implement an optimized converter, right? So make it super fast and super efficient. But however, you are kind of facing this n times n problem. There are so many combinations you can pick, and they don't share some common path. But we want to make this one simpler by introduce a standard data format in the middle. So this m times n complexity becomes m plus maybe 2. And the solution here, the proposed solution here is we definitely will use Spark to load everything. And then we standardize the data exchange upon a standard interface, so people only need to support, say, Spark can convert data into this Apache Arrow format. This is current proposed format. And then all the other kind of deep learning formats, if they can support Apache Arrow, they can do the conversion, then you don't have to build this m times n solutions, right? You only need m plus n. But it only works if introducing this Apache Arrow, introducing Spark in the middle, doesn't introduce a huge overhead. Because in both big data and AI, people care about performance a lot. And if you introduce a huge overhead, and people may not choose this option, people may say, hey, I have the data in MySQL, I want to convert them to TF records. I will just write my own converter, and I don't care. Right? So, but however, if the overhead is small, and let's say it only introduced 1%, 2% performance drop, and then people don't have to do this customized converters, they just use the existing ones. That will make just both community more focused on implementing their own support towards the standard format rather than just doing this a huge kind of pair combinations. But let's look at the problem, and let's say convert Parquet file to some TensorFlow dataset. So it seems that it's just really simple. Use Spark to read the Parquet file and then just write into some TF records, and that's it. Like two stages. And however, this is the real life. So it's a really long path where you convert some data, load data into Spark and convert it into just some other formats. First, your data sits as in Parquet format, and we will use a native Parquet reader to read and implement it in C++. And then the next one, well, it will get loaded into Spark, and Spark use Java, use JVM. And then this data, if we pick the arrow path, and will be converted into Apache arrow format. But this is still in JVM. But people just use Python for deep learning, right? So, and we need to convert the same arrow data into the Python process, and that's through a socket. And then we can convert this arrow into some pandas data frames, and pandas data frames becomes this TF data set. And at the very last step, you also need to load the data from CPU memory to GPU memory.
So how many copies of the data is this?
Here, this data is on disk, and this one you don't need to save the copy, right? So we just say stream, just send the data in a streaming fashion, and here depends on the implementation, and Spark can do this lazy evaluation that helps a little bit, and you may convert the record row by row. And even here in arrow, usually we do this row groups instead of sending over single records. We're sending a row group together to Python, and but usually when you hit here, pandas, and you may just say materialize the entire table and then get into TF dataset. You can also choose a batch fashion. So yeah, so even you don't install multiple copies, but still it's not super efficient. Then we need to think about how we are going to optimize this route. So the first one is, if we standardize the data exchange interface about just around Apache Arrow, we don't need to convert Arrow data into pandas. And maybe, if we have an implementation of TF datasets based on Arrow format, and we don't need this conversion, we can just reduce some overhead and put a shortcut from Arrow directly to TF dataset, right? So, and another one is a pretty interesting one. Is so because Spark, when you use data frames API, Spark kind of knows about what you want to do, right? So you described your query using data frames, and Spark knows the logical plan of your query, and Spark tries to optimize into some physical plan. And when Spark sees that, okay, you are going to load Parquet, and then you are going to use Python for the training, and then why we need JVM here, right? So why we need to send the data to JVM and then just pass the data from JVM to Python? And if Python can read Parquet directly, can I just make a shortcut when I do the query plan optimization, and then people can read Parquet files directly from the TF dataset, but Spark can still help here. For example, if you need certain credentials to read Parquet, and you need to access just encrypted storage, and Spark can still help and the Python process to read Parquet. But if you can do this shortcut, at least for this simple scenario, it will help a lot on the data performance, right? So those are the things we want to optimize, but definitely we also want to optimize each kind of arrow here, and we want to make them much, much faster. Yeah, and also for deep learning jobs, when you do model inference, it's usually you don't get a really good performance if you send the records row by row. Just make a single prediction and another single predictions. And modern hardware can utilize just multiple operations at the same time. So you definitely want to vectorize the computation and then get much, much better speed up. And in Spark 2.3, so 2.2 and 2.3, we introduced this pandas UDF, and it's kind of an implementation using Apache Arrow, but that can utilize vectorized computation, and we show really, really just a good speed up. And here, the blue bar is kind of if you do the computation row by row. And then the orange one, if you can see this, so it's using the vectorized pandas UDF, and it's very easy to get 200x speed up. And when you do deep learning, distributed deep learning inference, and this is definitely can help a lot. The next kind of optimization in this proposal is we want to do this data pipelining. And when you load the data from Spark, and then eventually want to do computation in GPUs, this is a simple choice on the left side. You load the data into one small batch, you read 1,000 rows, and then you send this batch to GPU, and GPU start computation, and then you wait until GPU finished, and then you start reading the next batch, and then send it to GPU. But you are wasting 50% here, 50% there, right? So, and when you do the data pipelining, you can actually fetch the first batch, send it to GPU while GPU is running, and you can start fetching the next batch. And that will help a lot. You can get a good utilization of both your CPU and GPU and your network. So this is a part of the data exchange proposal here. And the last one, how much time do I have? Okay. So the last part is, we talk about this hybrid cluster. Definitely we need GPU nodes and for distributed deep learning training, but we also need the normal data processing. So, but currently Spark doesn't really recognize, and there are some GPUs installed on the worker nodes, and Spark only knows how many CPU cores you have on this node. So, but when you do this, when you try to mix them, and Spark definitely need to know about the accelerators and not only GPU, but maybe FPGA, and installed on the worker nodes. And so Spark say, yeah, so Spark user can just specify what resources they need. And this is just an API pending discussion. It's definitely not the final one. And you can say, hey, RDD, I want to get accelerated by using some GPUs. And then at least I need 2 GPUs per task. And this kind of resource constraint is required. If you cannot find a GPU, a node with 2 GPUs, and please do not schedule this task. And you will be just running very, very slowly on other type of nodes. Or you can say this is optional. If you can find those nodes, definitely schedule the task on those nodes. But if you cannot, yeah, I can leave with CPU nodes. That's fine. So in this way, well, we can definitely just we can just let Spark recognize this those GPUs, and also if there are 2 tasks scheduled on the same node, and they need to figure out by themselves which GPU cards they can use, right? So for example, you have 4 GPUs on a single node. There are 2 tasks without communicating with each other, and they cannot really decide which GPU to use. And there is no easy way for them to communicate between each other because they don't even know each other, right? So only Spark knows. So then, well, once Spark understands the GPUs installed on the worker nodes, Spark can actually just distribute, doing the assignments of the accelerator, so task knows about it. And you don't need to worry about just competing against one GPU card while leaving the other one idle. Yep. So, and for this one, it's very similar. It's a community effort, and we also need to build support for different cluster managers, Yarn, Kubernetes measures. So for the timeline of this project, this is essentially kind of the very big change to Spark. And in Spark 2.4, we have this barrier execution mode already implemented, and we just cut the release branch, so people may be able to try the RC in maybe next week. And on Databricks, we're going to use this barrier execution mode to integrate with Harvard as a distributed deep learning framework we recommend to our customers. And this feature will be available on Databricks. And this is part of my demo, but people can watch videos offline. In the next release, hopefully the version will be Spark 3.0. So we try to have a production-ready barrier execution mode and have the majority of the data exchange implemented, and then also the accelerator-aware scheduling. So Spark currently runs 6-month development cycle. That means the next release may come maybe mid next year. So this is a community project. I definitely need help from the community members. So if you are familiar with Spark internals, and definitely please contribute your code. if just a Spark user, you can definitely try the bare execution mode or try our hardware integration and to see if it works well for your use case and send us feedback. And you can send feedback directly to the users as the Spark users list. So as I mentioned, yeah, this is really just a community effort, and many of the ideas are not new. They are just based on the past efforts and the brainstorming, and they just summarized here and put them together as a theme, and calling it Project Hydrogen here. Yeah, that's my talk. Please, any questions?
So from Databricks, there's another ML-related project, right? ML Flow.
Yep.
So what's the difference between these two?
So ML Flow is for experiment management and project management and model management. So ML Flow is targeting at the entire ML cycle, but it's kind of orthogonal to what kind of training algorithms you use. For example, well, once you use TensorFlow for training, and you can tell ML Flow, for this experiment, I'm using 3 layers, and for each layer, this is the size of the layer. And ML Flow will remember the parameters you use, the metrics you use, and later you kind of just go to the ML Flow UI and then to compare different models and try to figure out the best model. So in many cases, and if you just had some experience with model tuning, and you start with some basic parameters and start playing with the hyperparameters, and then yeah, you tried maybe 100 different combinations, you kind of feel, okay, the one I tried an hour ago, that was the best one, but I forgot the parameters I used. Right, so in this case, you can go back to ML Flow and you will remember the hyperparameter you used, the evaluation metrics, and even the model you saved. And then you can just easily just get the best model. You don't need to worry about you are forgetting the best model, right? So that's for mostly for the life cycle management of end-to-end ML pipeline. But this one is mostly for the actual training and the model inference part. They are orthogonal.
Thank you. So in terms of combining Spark big data processing and AI, how do you compare the Apache Spark and Apache Flink in terms of, especially for kind of online learning application?
So I think there are a couple articles online. The question is about Apache Spark and Apache Flink. And I think it depends. The first one is, I won't call Apache Spark is just a single project. It already became just ecosystem, right? So, and if you look at the data sources support and other just third-party packages, and this is a huge selection of packages you can pick. And then for, I think Flink community has been quite active for the past few years, but still it's in the just a starting stage. And if you look for the production use cases, and you may see some stories. But if you pick a framework, it's definitely to look at the community support, to look at the ecosystem.
You talked about a hybrid cluster with FPGA and GPUs, right?
Right.
So would a node manager running on each executor node need to become aware that these things are plugged in, or how would the Spark runtime discover them?
So currently, the workers, and each worker can report back to the Spark master and to say, hey, this is how many CPU cores I have. Right, so we just need to improve Spark worker, the slave, and so they can also report, I have 2 GPUs, I have 3 FPGAs, and back to the Spark driver, so Spark driver can coordinate.
Yeah, so the TensorFlow and Spark that you talked about several times, is that all the same Yahoo implementation? And if so, has it been optimized and made work more coherently with the existing Spark architecture? And then the next is, when this is all integrated, will you also have TensorFlow available with Spark integrated, and it would automatically work with accelerators such as GPUs? And the last in the series, will this be available as a service only from Databricks, or will it be pretty quickly available also, let's say, from Amazon and Microsoft and whatnot? And lastly, why Horvath? Why not someone?
Can I answer a question in the backward?
Yeah, sure.
The first question is, the last question was by Harvard. So there has been a really long kind of research effort about how to make distributed deep learning training faster. And in the past, people use a lot of synchronous way to just to train deep learning models. And in this way, and there's not much theoretical guarantee about the convergence rate. And then when you use 2 nodes, and you may see about 2x. But when it goes to 100 nodes, you kind of only see maybe 20x. That would be already just a pretty happy result. But eventually, well, you kind of see the slope going just being flat. So the difference between, for example, the Harvard and the distributed TensorFlow, the latter use models, just parameter server approach. So Harvard used a method called run or reduce. And essentially, it kind of the computation is about the same as you run this training on a single machine. And you know, if you are familiar with the mini batch gradient descent, and each worker will just accumulate the gradient, And if you do have just a parameter server, and you will try to update the global server in a synchronous approach. But Harvard will say, everyone stop after you finish one batch. And then report back and your accumulated model updates, and do a global sum, and then apply the computer gradient direction and determine the next model parameter. Globally, it's deterministic. And because this is essentially kind of the same as single machine and the mini batch gradient descent, there has some good theory to support it. So with Harvard, and based on their benchmark, even at cluster set 64, and they still not see about 70 to 80% of efficiency. That's really good. And the same algorithm, Harvard didn't really invent this algorithm. It's an old algorithm. I think the original paper was from Baidu Research, and to talk about how you use run or reduce and to optimize the deep learning training workload. So that's why we pick Harvard. And another reason we pick Harvard to do the first integration is Harvard works with multiple deep learning frameworks. Harvard doesn't do deep learning training. Harvard only adds some hooks. So when you calculate a gradient, and you tell Harvard to calculate the gradient, and you still send the result back to the backend. The backend could be TensorFlow, could be Keras, could be the reason they also supported PyTorch. So this is why we feel it's a kind of a nice framework to integrate with, and it provides delivers some good performance. So your previous the question before this one was the TensorFlow on Spark, right? So we at least many kind of integrations with deep learning and Spark, but they all hit the same issue about the Spark job scheduler. And because Spark doesn't really guarantee to give you 10 nodes at the same time, right? So before we have the barrier execution mode, and then that means, well, there's no kind of guarantee that you either waste resources, you hold all the existing slots until you have the enough slots to continue to start the training load, or well, you need to handle the fault tolerance in just a kind of hacky way. And with barrier execution mode, you can actually just say expect you have the same expected number of workers running at the same time. You have sufficient info and tooling to coordinate the workload. So I believe, well, once people can integrate with barrier execution mode, you will see much better integration. And from the community, I don't think it will be only Databricks. We will definitely do the integration with Harvard, but we also expect other integrations. And we do not expect end users to use the barrier API. It's very low-level API and on a daily basis. We expect developers to build the integration and on top. And the integration may not go to the Apache Spark main repository. And because, for example, if we pull in TensorFlow dependency, and then we need to manage what if there's a new release from TensorFlow, right? So Spark updates new releases every 6 months, but TensorFlow currently make new releases almost every month. So then, while user may end up with using old version of TensorFlow, so those integration may live outside Spark as a Spark package. Did I answer all your questions? Thank you.
Any other questions?
Slides on the
Okay.
slide share?
Yeah.
All right, give a big hand to Tushan Ray.